My project title is lookup-based CNN accelerator. After last presentation, I received Professor Zhang's advice, and following his advice, I did some exploration. We have known that CNN is accurate and well, but it's computational expensive, and CNN needs frequent memory access. For example, AlexNet is a version of CNN. AlexNet needs 61 million parameters and 1.5 billion float point operations. So for mobile device to running this CNNs, so it's very challenging. So for mobile platform, you need to speed up. In software level, you can use LCN to replace CNN to speed up the. And in hardware level, you can use GPU, PDA, or some other ASIC accelerator. I explored 3 models. The first model is running CNN on mobile CPU and GPU. And then I try to run LCN on mobile CPU and GPU. And last, I run the LCN on the 3DICT, which is the model we proposed. You can see.
Before stepping into the detail, could you please introduce some basics on the CNN and the LCN?
Okay. We can introduce LCN. For the
CNN first.
For the basic
CNN first.
Okay. For CNN, it is comprised of the almost 3.
You have the picture in the previous slides, right? Yeah.
This one?
Yeah. Can you briefly introduce the parameters in this figure? How to do a convolution?
Okay. The parameters refers to the kernel. You can see the K by K is kernel. So the 61 million parameters represents, for the AlexNet, you need to, this width is matrix. If you want to do a convolution, I can draw on the board. This is the input image. Now this is pixel. This is your kernel. Maybe it's 2 by 2. Then first you need to map your kernel on your input. You can map your kernel on your input on this 4 pixels. Then you can call this 1, 2, 3, 4 pixels. So you need to multiply your first pixel you input with your first pixel in your kernel. multiply the second pixel of your input with your kernel pixels, and then you can get one output pixels. So which is one convolutional operation, and then you need to move your kernel to right side. Then your kernel, the position is like this. So every convolution operation, you need to move your kernel one step, and until you scan your input, you scan all of your input, then you can get output. So you will find that the width of your output equal to W minus K plus 1. If your move spread is 1, then your output width is W minus K plus 1. So for us that this 1.5 billion float point operations means that you do how many numbers of your multiply and add operations. Does anyone have a question? So for the LCN, the weight firstly is decomposed to three matrices. The first matrix is D. The D you can call it dictionary. In traditional CNN, in one layer there are many widths, and these widths are different. But for the LCN, in one layer there is only one matrix, which is D. So the D is a shared dictionary. So you can reduce a lot of parameters, and you can reduce some float point operations. The lookup based means that you need to look up the shared dictionary instead of to do all the convolution with the traditional ways. So I explored these three models. In this bar graph, you can see that for the CPU, the x-axis represents the hardware platform, such as CPU, GPU. The y-axis represents the frames. So the black bar represents the frames per second per watt, and the white bar represents the abstract frames per second. You can think the FPS as a performance, and the FPS per watt is a power matrix.
What's FPS?
It's frames per second. One frame refers one image. You know, your input is one image. If 1 FPS means your machine can process this one image during 1 second. It's a throughput of your machine. One point I want to say is that for the GPU, you can see that the white bar is relatively high, but for the black bar, represents the FPS per watt is relatively low. At least it's less than the 3-digit. You can see that, which means that for the GPU, the performance is good, but they cannot meet the tight power budget at mobile device. So we need to design another hardware accelerator to deal with this problem. But for the 3-digit based accelerator, although its performance and power can meet the requirement, the 3-digit has a problem, which is endurance. The reason of the endurance is that you need to map and write your weight many times onto your hardware. You can see that this graph. I have showed this graph last presentation. This is a vector, and this is your matrix, your kernel, in every layer of UCNN. You need to map your kernel to this hardware IRAM cross bar. Because in your mobile device, the number of this array is very limited because of the power budget. So in every layer, you need to rewrite your matrix onto this IRAM crossbar many times. So this cell will be done if you write it many times. So this is the reason of endurance. There are some solutions to solve this problem. For example, you can enlarge hardware memory. I mean, you can add another this array. If you use 2 times array, then you can improve your endurance of memory 2 times. But you know that if you add another array, then your power will be added at the same time. So I won't take this method. The second method is you can use LCN, like I have said. LCN can reduce your weight, so you can reduce the writing number of your memory cell. The last method is you can use 3-dimensional IRAM crossbar to balance your writing. Like this picture showed, this is a 2-dictionary IRAM crossbar. Then you can use the 3-dictionary. Then using the baseline to to balance your write. From this bar graph, you can see that the y-axis represents the endurance. For this, from this first bar graph to the fourth bar graph, you can see that their endurance is less than 1 year. Almost even for this is less half a year. So it doesn't work in real world. Then you can use the second solution and the third solution, and then you will find that its endurance is almost 100 years. Maybe you don't need so many times. Maybe 100 years is very long for you. You don't need that. Because there is a trade-off between your performance and your endurance for LCN, so you can improve your performance at the cost of some endurance. So for the last bar, you can reduce your endurance and get some better performance. So my experimental modeling is used FODLOM, this simulation tool. For this FODLOM, there are two inputs. The first input is user-defined accelerator, such as our 3-digit. And then the second input is your benchmark, your network. Then the FODLOM can deploy your neural network on this your defined accelerator. Then it can output the performance and power. So like this picture shows, this is the accelerator, this is your performance, your power efficiency. You can see that these two are our 3-digit, and these are previous hardware accelerator. So you can see that our performance and the power efficiency is better than the previous hardware accelerator. So does anyone have a question?
I might be wrong with the question itself.
Okay.
But the first frames per second you mentioned, that happens to video files, right? But how do you convey, like, use the same metric for if you're doing image, like a chronology file?
Yeah, good question. Actually, the frames per second in traditional refers to the video, right? But you can think a situation. You need to recognize a lot of images. Then you input a lot of images to your machine, and your machine processes this tens of images one by one. Then,
so it's basically the speed of the processing of each image.
yes.
So we can consider frames per second as images per
Yes.
second.
So if your inputs are many images, it's very similar to the video, right?
anyone who can understand, honestly, who can understand his work? Can you say something? If you can do that, I will give you some extra credit.
I understood the one graph where you're talking about the different memory lifetimes. You talked about the different memory technologies. Is that something that they were concerned? Was that a primary concern? They wanted to run the neural network for that many years?
Sorry?
I guess it was more of a question, not necessarily saying that I understand it. But what is the purpose of this graph for you? Were they trying to say that they wanted to run hardware for over 10 years?
Yes. The purpose of this graph is to illustrate that for the real application of your design, you need to consider your lifespan, right? I mean, if you use this hardware platform, you need to write your like memory. You need to write or store your weight on this cell. You can store an element. If you write this cell many times, maybe this cell will die.
All right, so I took that point of view. The ReRAM would last longer if you built your hardware with the ReRAM. Correct.
Yes.
Okay, so yeah, in order to finish your project, of course, you need to do a lot of very hard work, finish a lot of the technical part. But what's more important is how to sell your story, how to sell your project. So basically, he is trying to architect another accelerator for a simplified CNN model. This is the original CNN model. So in order to do a convolution, in order to test one image, you need to have 60 million weights, and you need to perform this amount of multiply accumulation. And then some smart AI guy proposed another CNN architecture, which is a so-called lookup table-based method. So basically, they reduce the amount of weights into a small dictionary. First, you need to do the convolution between this dictionary and your inputs. And then you get a semi-dictionary. You do lookup and scale operation on that semi-dictionary. What he found is that if you use the original weights in the small mobile devices, you don't have so many arrays, so many cells to do that. What you can do is to update the cell G, which is the content in the cell. You need to update, you need to write your weight into this array, and then do the convolution, and then do the dot product operation. But here is that you update the weight, in the weights in the array so frequently, but the array only has a limited endurance. In this way, your array may fail maybe 1 day or 1 month. So he found that instead of writing the original array into this, the original weight into this array, you can write the small dictionary. Compared to 60 million weights, the dictionary is really small. So in this way, you actually write less content in these cells. That's the reason you have a longer endurance. Yeah, I hope besides the technical part, you can practice the presentation part. Anyone have some other question? Maybe next group.